Hello everyone. Today I am going to discuss a specific topic of atomic structure, which is how to determine term symbol of any states. So before I jump into term symbol, let's talk about what is term symbol. So in atomic structure, we have already learned about there are some specific electronic configurations of different atoms, right? Let's talk about one example like oxygen. Oxygen, how many electrons are there? Oxygen is 8, 16. So we have already learned in quantum mechanical model, electronic configuration of oxygen will be 1s2, 2s2, 2p4, right? So according to this electronic configuration, the electrons will be distributed in oxygen. There is a nucleus and like s orbital and some like here in the s orbital 2 electrons, another s orbital 2 electrons. Also in p orbitals, like there are 3 p orbitals possible, right? X axis, y axis and z axis. In among 3 orbitals, 4 electrons will be distributed. If I draw a box structure for p orbitals for 2p, so 1, 2, 3 and 4. Total 4 electron will be distributed in, if it is px, py and pz, px, py, pz in 3 p orbitals. So now we have to understand that electrons are distributed inside an atom, that's all right, but what is the state, like how to represent this whole scenario of an atom? That representation of electronic state is called as term symbol. So for now, let's say this is the ground state of the oxygen atom, because when we are electronic configuration, when we are writing like this, then electrons are highly stable. If we write 1s2, 2s2, 2p3 and then 3s1 or 1s2, 2s2, 2p3, 3p1, something like that. So electron jumped from here to here, or it overlooked s orbital, jumped in p orbital. This kind of awkward situation when electron jumped over higher orbital has higher energy of the state. So these electronic configurations also have a specific state. And the previous one, this is the lowest possible electronic configurations. How to write this electronic configuration you have already learned in Aufbau principle, using something like 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 5g, 6s, 6p. So first, according to Aufbau principle, first we are going to put electron in 1s, then in 2s, then in 2p, then 3s, something like that we are going to follow. So this Aufbau principle tells us how to get the ground state electronic configuration. Now we have to determine that how to represent that ground state electronic configuration in a single representation or single letter instead of writing whole electrons. Okay, so let's try to see how to get that term symbol using a simplest method. Here in the term symbol sequence, we need to understand three different things. One is spin angular momentum. Spin angular momentum is represented as capital S. Let's take the example of the oxygen atom. Oxygen atom, we knew the electronic configuration is 1s2, 2s2, 2p4. That means in outer shell there are 4 electrons. Let's draw it to make it more clear. 4 electrons. Now, can you guess that what is the spin of this electron? You can clearly see I have drawn 3 electrons upwards and 1 electron downwards. So we already know electrons has 2 possible spin. One is plus half, one is minus half. These two are the possibilities according to magnetic quantum number. So this plus half and minus half. So if we consider these 3 upside are plus half, then we are getting 3 plus half, right? And we are getting 1 minus half. So if we are going to add all of them, what will be the total outcome? What will be the total spin? So 1 plus half, 1 minus half will be cancelled out. Total will get 1. Half plus half is 1. So that is the spin angular momentum of oxygen in the outer shell. Other things, if we think of 2s orbital and 1s orbital, you can see one is plus half, another is minus half. Spin angular momentum are totally cancelled out. So we don't need to calculate those. Those are 0. But here we are getting some spin value here, that is plus 1. So spin angular momentum is the total spin of a system, of an atom, specifically outermost shell. Otherwise, inner shells are fully occupied. So we are getting total spin of the inner shell is 0. Now, what is spin multiplicity? You can think of one important thing. I have drawn this picture like this. I could have drawn 2p4 like this. Up, 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 down. Or I could have write this. Up, 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 down. And also the trivial one that what I have drawn previously, this one, right? Up, down, up, up. So you can see that spin down electron can be 3 different positions, first, second or third. So there are total 3 different scenarios for this kind of specific situation. So 3 different scenario means 3 different possible state. This is called spin degeneracy. So this spin degeneracy is implying that total spin multiplicity. So what is spin multiplicity? So spin multiplicity is nothing but 2 into total spin angular momentum plus 1. Let's take an example where for oxygen O816 S we got plus 1. So 2s plus 1 is giving 2 into 1 plus 1, 3. That is the 3 possible state implying the total spin multiplicity. So far so good, I think. So if you have any doubt or questions, you can definitely discuss here. That what we are learning here, we are trying to understand electrons are spinning inside, that we don't know how, but that spin creating a angular momentum, and we are trying to calculate the values in terms of a quantum number, that what is the value of that angular momentum. Total spin angular momentum for oxygen atom, if we write it oxygen 816, for oxygen atom is 1, because 1 is like 3 electrons configuration are upside spinning, another is the opposite spinning. So 1 is cancelled out and 2 are remaining, giving 1. And then when we are putting the formula in spin multiplicity, we are getting 3, which implying that in specific scenario we are getting 3 different states. That's why. So now this is the spin angular momentum we have talked about. now we need to understand another specific term which is called total angular momentum of that orbital angular momentum. Like this is the electronic spin, but electrons, let me write it down, orbital angular. So orbital angular momentum. What is orbital angular momentum? Let me draw something to make you more visualize. Here, let's remove this one and think of that these are p orbitals. So if I draw p orbitals like that, so actually electron are spinning in that orbital somehow. In Bohr's model, it is more easier to visualize. Like if you can think of, if it is a nucleus and electron is moving, so electron can create an angular momentum because charge is moving. Similarly, in p orbital also, electrons are somehow moving in that orbital and creating an angular momentum. If a charged particle moves, it has an angular momentum, of course, right? So it is creating an angular momentum. So that is the orbital angular momentum which every electron has, because it is in an orbital and it is constantly moving. So what is that orbital angular momentum for a specific atom? We have to calculate. Let's try to calculate for oxygen. One important thing we need to understand that we already know. For oxygen, let's talk about n values. This one is 2, 1 is n equal to 1, 2 is n equal to 2, here also 2p n equal to 2, that we already know, that is called principal quantum number. Secondly, which is azimuthal quantum number, represent as L, is for here s orbital L is 0, another s orbital L is 0, but for p there are 3 different L's. L is 3 different values, from which to what? From 0 to up to n minus 1. So here when n is 2, we are getting 0, 1. These two L values. And for these two L values here, we can write according to the angular momentum quantum number, the magnetic quantum number, plus 1, 0, minus 1. Why? Because magnetic quantum number you already know is from minus L to up to 0 to ... plus L. These are the possible values, and I am assuming that this basic quantum number region you already know how to calculate these quantum numbers values, what are the boundaries, what are the range, we have already learned so far. I am assuming, and now I am just going forward to letting you know what are the values. Here L is 0, M is 0, but here magnetic quantum number has 3 different values, plus 1, 0, minus 1, which is representing the angular momentum in presence of some magnetic field. So now if we want to calculate the total angular momentum in p orbital or s orbital you can see there is no angular momentum values, because the value is giving, quantum value is giving 0. So it is not giving any angular momentum. How to visualize it? You can think of a spherical ball. If it is moving everywhere, like in a sphere, like if electron is moving in a sphere, it is moving every possible direction, right? 3-dimensional. So every possible direction making a angular momentum which creating the net value 0. That's why when a spherical movement is happening every direction, total angular momentum is always 0. That's why fulfilled situation when p orbitals are totally fulfilled, px, py and pz, you can think of it is a spherical situation or symmetric situation, and every fulfilled situation total angular momentum gives 0. This is a very important thing, you can note it down. So now let's calculate what is the angular momentum of this situation. Okay, so let me omit this thing. And now total angular momentum of this p orbital, because these are 0, is total, if we represent total angular momentum L, it is giving, you can think of one electron is +1, another electron is 0, another electron is -1, also another electron is +1. -1 +1 will be cancelled out, it will give you +1. Why? Because electron are in which orbital, that is their quantum values, right? So in first orbital there are 2 electrons, so double +1. In the second orbital there are 1 electron and the value is 0, so +0. And the third orbital only 1 electron and the value is -1, so 1 -1. Overall, this is the total angular momentum. That means when an electron are there in these orbitals, it is giving overall net angular momentum +1, because one electron and another electron are cancelled out, and these electrons are not generating any angular momentum. Remaining angular momentum is only +1 for this oxygen case. Understood? So orbital angular momentum, total angular momentum represent as capital L is giving +1. Understood what I have done? For oxygen we are taking the example. Okay, so far so good. Let's stop here and let me put some ink inside my pen and then we'll start from here. Thank you. So we are talking about the orbital angular momentum. So orbital angular momentum are different representations. Like L, if we got 0, then we can denote this as capital S. If we get it as +1, it is capital P. When we are getting it +2, it is capital D. Similarly, for 3, 4, so far, so on. S, 3, D, F, G, H, something like that. So these are the notation. For oxygen, we got L equal to +1, which we can represent as P. Okay. So now let's talk about another important thing, which is total spin orbit coupling momentum value. What is spin orbit coupling value? First of all, we have discussed that electrons are spinning. That is an intrinsic property. We don't know how it looks like, but we know because of that electronic spin we are getting an momentum, angular momentum, right? Also, electron are rotating in an orbital. So because of that rotation, it is also creating another angular momentum. Now the question is, if these angular momentum are in the same direction, it will add up. If they are in opposite direction, they will cancel each other or they will subtract each other. And if there is some random direction, something like upside, someone is upside, someone is something like that, so they will do the vector interaction. So this angular momentum, spin and orbital, they are interacting with each other to give a specific energy states. Actually, the energy for angular momentum, spin orbit coupling angular momentum, energy is proportional to that spin vector as well as that angular momentum vector, and is proportionality constant. We can think of a lambda So this situation, the depending on lambda is if lambda is less than 0, is lambda is negative, then the total energy of the system only be negative means stable, negative or lower means stable. The total energy of the system will be more stable if this coupling is positive, and positive coupling happens only when L plus L quantum numbers are adding together. Also you can think of, if lambda is greater than 0, then the coefficient, the lambda value is positive, but total system has to be negative, or system has to be as minimal as possible. So this coupling has to be opposite to make total energy less, to minimize the energy. That's why this coupling value has to be negative or minimal. How to get this minimal value? When L and S are opposite to each other, subtracting each other, making it minimal. And we have taken the mod value. Why? Because we don't know that what is the total outcome we are getting overall resultant, not the direction. Okay, to make that overall system as minimal as possible. So these two scenarios are the coupling between spin angular momentum and orbital angular momentum. So these spin orbit coupling values we can write down as a new constant which is called J. There are third scenario which I did not mention. Lambda could be 0 as well. In that case, energy is 0, or we can think of, if the spin angular momentum or orbital angular momentum, any of them is 0, overall energy can be 0. So there is a third scenario where J is S or L only, where the one or other is 0. S plus L, if L is 0 is giving S, or if S is 0 it is giving L. So S or L only if one of them is 0. The other way around for the minus system. So now what we have to memorize? This spin orbit coupling values. Let me tell you how to memorize that which situation will be which. If let's talk about p orbital. If the orbital is less than half filled, then what we will use? We will use L minus S, that is the J value. And if it is more than half filled, something like that, then we will take the J value as L plus S. Now what about the half filled situation? Like this, you can see that here plus 1 0 minus 1 L, total L is plus 1 minus 1 0 is 0. So L is already 0. So L is 0 means J is nothing but S. So half filled situation will give the spin values only. And what is the spin values here? You can think of, if plus half plus half plus half, so plus 3 by 2, something like that. So there are, for this specific example, for less than half filled we will use this formula, for more than half filled we will use this formula, and for perfectly half filled here J is equal to S. This here, that for specific example P we are getting 3 by 2. So what is the summary? What is the summary of total system? So how to write a term symbol? Let's summarize every single thing we have discussed so far. So in conclusion, term symbol of any state can be represented as total spin multiplicity, which I have already told you, 2s plus 1 here, and then total angular momentum upside 2s plus 1, then total angular momentum, and then spin orbit coupling value. this is the term symbol of any atom or any states. Now let's take this previous example which I was discussing, oxygen 8. Here we already know that spin value here is total S is plus half, plus half, plus half, and another is minus half, plus half, plus half, plus half, minus half is giving 1. So 2s plus 1 giving 3. Now for L values, plus 1, 0, minus 1. Plus 1 has 2 electrons, plus 0 has 1 electron, plus minus 1 has 1 electron. It's giving everything is minus 1 plus 2, this is giving plus 1. So for L equal to plus 1, I have told you the symbol will be capital P. And for J, is this more than half filled or less than half filled? Clearly this is more than half filled. So J will be L plus S. The value is L is 1 and S is also 1. It's giving 2. Therefore the term symbol here will be S plus 1 is 3. L value here symbol is P and J value is 3P. So if someone asks what is the ground state term symbol of oxygen atom, electronic configuration is this, and we have to tell by calculating this it is 3p2. Okay, that's all. Next we will give some example and try to solve some other term symbols in future. Okay, thank you.